contacts, and we also charge them by induction. So if you want to charge by contacts, the word contacts means they must touch. The word induction means do not touch. Just bring close. And most times when you want to charge by contacts or by induction, you need a charged body. So to charge by, I'm being slow like this because of some of you that might just be there, but I might not give notes. But if you are following what I'm saying, it's not that hard. So you charge a body, a conductor, by either by contact or by induction. And that body you want to charge needs what? A charged body. This is what I'm saying. You have, then another thing you need to know. Let's first do the example. So you take a metal like this. This metal is on an insulating stand. This one is an insulator. Without wasting time, let's just make this one positive, positive, negative, positive, negative, and negative. Now this material, is it charged or neutral? Neutral. So now this is a neutral material. But I can make this material to become charged by contacts. How do I make it charged by contacts? Let me bring a negative material. Then one thing you should remember is this. From the law of electrostatics, like charges repel, unlike charges attract. That's a rule that you have all had at a point in time before, Abby. So, like charges repel, if I bring a negative close to a negative, what will happen? They will repel, they will run away from each other. That's what that means. So, let's say I bring, which one did I make negative now? If I bring this ebonite rod close to a biro, you will see that both the biro and the rod will go away from each other. But if I bring a ebonite rod close to a glass rod, you will see that they will attract, all because of what they are carrying. So like charges repel, unlike charges attract. So from what we have here, you take a negative charge body. This guy is carrying negative, Abby. That means it is what? It is charged. I want to charge this body. That's why I said you need what? A charged body to charge another body. You need someone that knows book to charge someone that does not know. So from what we have here, that charged body, when you use it to touch this, something will happen. Another thing you need to note, and don't be deceived by it, is that only electron moves. That's another point you need to note. If materials are touching each other and we are saying one is acquiring this and acquiring that, only electron moves, protons don't move. Abby, where are protons? In the nucleus, right? And they don't leave nucleus. It's only electrons that keeps what? Moving around. Is that taking? So now, if I'm saying that this guy will touch this guy, don't ever in your life say it that and the positive charge will enter. Don't ever say that, because protons don't what? I'm only showing the distribution just to make it easier. So protons don't move. Now, if I bring this negative charge to touch this guy, what will happen? All the negative here, what will happen to them? They will run away, Abby. So they will move away from that part's negative charge. If you are here for probably JAM class or SSC, or you are a younger junior generation, just know that this class is an advantage to you. You might not get everything all right, but it gives you a background knowledge, and the background knowledge can make you to quickly get things better, which is an opportunity for you. But if you are a post-UTME student, some things should not be new to you, if I'm saying it. But as much as possible, the extent of this is for you. But pay attention. I don't think anything I've been saying is so strange that anybody shouldn't be able to get, except you have never even done atomic structure in your life before. So now when this guy touch this guy, what will happen to all of this negative? They will run away. We already said like charges do what? Repel. So negative will repel negative. So eventually, while they are still touching, all of those negatives on this other guy, they stay away as far as possible, and the positive now stay. Now, at the end of the day, what will you notice? I won't repeat this again, please pay attention, because it will waste our time if I have to repeat it over and over. Now, when this negative is touching this thing, because of the positive, you know, this negative, they have to stay away, Abby. Because of the positive that are accumulating here, they will, you know, they are touching. So the negative from here will enter here, because there are a lot of positive here. She gets. So now, when the negative enter, maybe two can enter. If two enter, what will happen to this guy? So let me redraw another one. This positive charge is here, and this negative charge is here. You can't see. You can't see here. Okay, I'll write at the top. But let's manage this one through first. So negatively charged, because there are two negatives, Abby, that you can see now from what I'm indicating. Now, there's a reason I'm asking that question. If you now look at how many negative charge is this one compared to this? From what you can see here, how many negative charge is this to this? How many negative charges has this one acquired? Let me put the English down. You know, one positive will neutralize one negative, Abby. So if I want to rub it, I can just, because I want you to see the process, that's why I'm seeing indicating positive, positive. Now, this one acquired 2 electrons, Abby. This one also has what? 2 electrons. That's why 2 negatives are here. I hope you are following. So from what we have here, this one has 2 negative. There are 3 positive, 3 negative. That's neutral. Abby, what is he having in excess? 2 negative. She gets. So now these 2 negative and these 2 negative, they do what? They balance out. So do you think negative should still continue to enter if this one has 2 and this one has 2? They are now balanced. Abby, which means that this one cannot gain more than this one. It's either it gains less or it gains equal charges. Do you get that? You know, if this one gives you 3, this one will now become just 1. And at the end, if they are still touching, what do you think will happen? This one will come back inside here. Do you get that point I'm trying to make clear? Don't go. So now, from what we have here now, at the end of the day, this one becomes negatively charged. And this one also becomes what? Negatively charged. So what did you notice? There are 2 questions they can ask you here. When you are charging by contacts, for general knowledge, they must always what? Touch. Abby? Number 2 is that when you are charging by contacts, the charge body will acquire the same charge as the what? As the neutral body. What did I bring close to this guy to touch it? Which one did I bring close to this guy? Is it negative or positive? Negative. At the end of the day, what did this guy acquire? Negative. So when you are charging by contacts, if you charge by negative, that one you are charging will acquire negative. If you charge by positive, that one will also acquire what? Positive. Is that taken? That's what this statement means. Let me quickly do this. I'm not trying to waste time, but I think some of you might need help. So from what we have here now, this guy is neutral. Now, if they are touching, what do you think will happen here? I will not carry you along again. Where we did it from here to here, from here to here. We did it from here to here, or from here to here. Because we said only electron moves, not proton. So the charges will run from B to A. And at the end of the day, when negative enter here, this will become more positive. Abi, that means that you are using positive to charge, and this will become positive eventually. Do you get that? So that's what these statements mean. Another thing you need to know is that electron gain is either less than or equal to the electron loss. I don't know if that statement sounds clear. The electron gain will be either less than, you know, it's a class that we want to quickly end. That's why I'm using shorthand and not stories. But everything I've said is in your stories. You have to learn a lot of things. So now I said the electron gain must be less than or equal to what? The electron loss. You know, in this case now, how many electron was gained? 2. How many did this one lose? 2. And at the end of the day, they will what? Balance. Abi. But this one cannot lose 3 electrons. And this one will now have 3 and this will now have 1. It's no longer going to be balanced. Do you get that? So that's that point. So let's go to induction. Induction is where you need to now pay attention. So when you are charging by induction, we need a wall clock here. So when you are charging by induction, what did we say they should not do? They should not touch. You only bring close. So there are 4 steps you use in induction. So let's say this is the body we want to charge now. Positive, 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 negative, negative. Now this body is what? Neutral. Abi? I'm bringing the negative charge closer. Please pay attention here to induction. The difference between this and this is just that this one they always touch, this one they do not what? They do not touch. So now when I bring this one closer to this, what did you notice here now? This one is what? Negatively charged. This one is what? Neutral. Abi? Now, because I'm bringing this closer, they are not touching. What will happen to the negative for these ones? Abi? So step 1 is bring closer. That's the step 1. So you bring the charged body closer. The body that is charged, you bring it closer. Step 2, you will notice something. Because they are not touching, even though this one is feeling it that there is negative around, all those negative are brought to one side. Abi? All the negative they are brought to one side. And this guy is actually feeling it. But you know, this negative cannot run and enter. Why can it not enter? They are not touching. Do you get? If they are touching, the negative would have run inside. So the next thing is that this is step 1 now. Step 2, we have what we call earthing or grounding. Earthing simply means that you will touch this guy, or you see a symbol like this. When you see a symbol like this, it means you are discharging something. Now, you touching it, you are also a conductor. The moment you touch this guy, what will happen to all of those negatives? They are looking for where to run because this guy is threatening them. So they want to run. So the moment you touch, you know, these are insulators, so they cannot run down. That's why I label this as insulator the other time. So they can't run down because it does not conduct. But by the time you touch, you are a conductor. That's what this symbol means. All these charges will just run through your body and run to the earth. You know, the earth is a conductor and all of those things. So now, when all of these things run down, the 3 have left the body. Abi? So that is step 2, earthing. Step 3, you remove the earth. So in step 3, while the negative charges run down, you know, this one is not touching, so it's just remaining there. You make sure that that guy remains in its position. Then all the negative charges will run down. So you have removed the earth now. So that's step 3. Remove earthing. They can ask you to arrange them in that chronological order, and it might be your test after this class. So you remove them by heading, and I'm going to deal with you if you do rubbish in the test. So now, by heading, all of these negative charges will do what? Will run down. And at the end of the day, what do we have left? Positive, Babi. You know they are not touching. If they are touching, what would have happened? As this one is positive, the negative would have entered. So the last step, which is the fourth step, is you now separate them. Separate them. So when you now separate them, now this would have been this, and this would have been this. So let me quickly explain that again for the sake of those that did not see. So by induction, what do? You bring the charged body closer, Abby. Don't allow them to touch. Then what will happen? The effects of this one will be felt by the neutral body. And all the negative inside this one will run to one side. Because like charges will do what? Will repel. So they run to one side. Do you get that? That's step one. Bring them closer. Step one. Step two, heads. When the negative charges are on one side, you touch it with a finger. They can put that in your notes. You touch with a finger. That's what heading means. So the charges are looking for where to run. So what do? They run through your body. When you touch through the finger, you can't get electrocuted. So now, the next thing is, when they run out, what do? Now you now remove heading. So you remove your finger. Why this guy is still where it is? Do you get that? Now, when you remove your finger, you know you have channeled those electrons out. At the end of the day, you're having positive here. Do you get that? So now, the fourth thing is now to separate the two of them. At the end of the day, this would have been what? Positively charged, and this would have been negatively charged. So we call this process induction. Now, what did you notice by induction compared to contacts? Is it the same charges they acquire? So they acquire what? So if a question says that you are charging the body by induction, by bringing a positive charge closer, that means that body you are charging will acquire a negative charge. So you always get opposite charges. Opposite charges by induction. And what are the four steps involved? Number one, bring the charged body closer to the neutral body. Step one. Step two, head the body by contact or by touching. Step three, remove what? Heading. If you misplace them, then you are wrong. So, and they can ask you that why is it that this body must continue to be in place? Why it is there? You know that if I remove this body, look at it. So, let's say when I'm touching it, I now remove this body. What do you think will happen? All those electrons are left, they will run back inside. The major reason this electron are run is because this guy is closer. So they are trying to stay away from this one as far as possible. But if I remove this guy and I'm still touching it, I know I'm a conductor too, and this guy is positively charged. As I'm touching, that's by contact. So it will take all the electrons from my body and it will go neutral again. Do you get that? So you don't separate this until you are done. So separation is always the what? The last. So you can do this on your own. So that's by charging. So the next thing we'll move on to. My time is actually up for electrostatics. So the next thing we move on to is by, you can do this on your own. Bring a positive charge closer to a neutral body. And follow the steps and let's see what will happen. But naturally, if you see a question like this, if you bring a positive charge closer, not touching, what will this neutral body acquire? Negative. So they will always acquire opposite charges. If your first time in class, everything might still be looking strange. It is consistency that will make you alright. So just practice. Don't worry. If you practice, you will get it. If I don't practice, I won't know it. That's just the fact. So now, the next thing to talk about is, okay, I've charged this body now. I charged a body. That body is positively charged. But you know this positive charge is internal. I charge a body is negatively charged. This body that is negatively charged, I can't just look at it and say it is negatively charged. I must be able to tell by an experiment. So how do I tell that this body is negative? You know, this body now, I'm not even indicating it. And now say, is this body positively charged? You can't tell because you can't see it, Abby. So now, but I now want to test. I want to know if it is positively or negatively charged. Then we have what we call tests for charges. Testing for charges, and you test for magnitude. That means that you don't expect a charge that is like 10 positive to behave the same way a charge with 3 positive will behave. You will see that. So how do you test for charges? You want to know the sign of the charges. Is it positive or negative? Is it much or less? Then we use an instrument to test for charges. That instrument is called a gold leaf electroscope. For the first timer, it is a gold leaf electroscope. That's what we use to test for charges. I hope you're following. So you test for charges using what? A gold leaf electroscope. Now, this gold leaf electroscope, you need to note one thing. Before you use it, it must be charged. You don't use a neutral one. The gold leaf electroscope must be what? Charged before you use it. How will you charge it? You can either charge it by contact or by induction. And without wasting time, let me show you what a gold leaf electroscope looks like. You all can see this. This is just a simple diagram. This is made up of a metal disc. A metal disc. This is like a glass that you can see through, and it has this one is like an insulator, so that it does not keep transferring the charges. Now this is what it looks. These are the legs. These legs are the ones we call gold leaves. Gold leaves. So sorry, I'm writing down there. So now, this gold leaves electroscope, as it is, you can see these two legs are closing. It's because it is neutral. So let's quickly look at something about that. Now, for your gold leaf, if I charge this gold leaf by contacts, I charge it with a positive charge. I will not express that. What do you think? Naturally, let me just put this one here. Like this is the gold leaf now. This is a gold leaf. If you carefully look at what I've written here, you see that this guy is neutral. You can go and check it on your own. This guy is neutral. But in order to use it to test for charges, I cannot use a neutral one. I must charge that neutral one by contacts or by what? By induction. I hope you're following. Now, if I'm charging it by positive charge, what charge do you think the gold leaf will acquire? So I'm charging it by contacts. What charge will they acquire? So if you look at this guy, these legs can move. It's like a baby with two legs. They can move. Now if it acquires positive, let's say this is how it now looks like. Positive means there are more proton than what? Than neutron. So let me open it straight. You see the leg like this because of something. Let's say it has lost 4 electrons and the rest are still remaining positive, positive, negative, negative. Please listen to this, so that's what will make you understand it. Now look at this guy here and look at this guy. Here your number of proton is equal to number of electrons. Now this is where you use to ask you questions most. You are writing it. They like asking divergence questions almost every time. Is there space for her? Matilda, Mandela, Martha, Is there space there? There's a long chair now, you should take 6. You have 5 now, show to more 1, 2, 3. Oh, okay, I'll come. Are you okay? Are you sure? Please make her comfortable. 4. I would have said you go and sit at the back because you came late. You look too young to and fully class. Should I send one of them to the yeah. Create so that you don't waste our time. You have a space for her. Is it the longer chair that is space beside you? It's resting now. I'm the only one that can go through that sort of stress. Why did you call it? You people should not choke out. Give us space for other people. You are bad, think or joke. So please, let's quickly move on. So if you notice something here, the number of electrons is equal to number of protons. Yeah, number of protons is greater than number of electrons. And why is this leg open? Like charges will repel, Abby. So the positive here and the positive here, they will send each other away, and that's why that leg is so. It's very important. When that leg opens, we call it divergence. When the leg closes, we call it convergence. Is that taken? So now, let's now move on. If I charge it by induction, and I'm bringing a negative charge closer, what will it acquire? Positive, Abby. So, but we can make it to also acquire negative. If it acquires negative, that means there will be more negative below, and there will be other parts everywhere. There can be positive here too, just for big class. So now, this guy has more number of electrons than the number of what? Protons. So now I want to test. Let's quickly do a test. So my gold leaves are charged. Now, if you use a neutral one, you will get the result, and you will see why. But you need to use what? A charged one. So now, I want to test for a charge. So let's say I have a body like this. This body is negatively charged. I bring it closer to a charged gold leaf electroscope. This charged gold leaf, let's say it is positively charged. From what you can see, there are other charges, but I don't want to waste time. So from what you can see here now, look at this. This is the body I want to test. This is the gold leaf electroscope, and it's even a charged gold leaf electroscope. Now, by the time I bring the negative charge closer, what do you think will happen to this guy? Immediately I bring it closer, all the negatives that are up here, what will happen to them? You know, they want to stay away from this one as far as possible, so they will run down. And by the time they run down, that means that if one negative come and join this, you know, a negative and a positive, that's neutral. Let me remove that. It should come down again, that means this one will go. If another negative comes down, that means this one will go. At the end of the day, all the positive have reduced. And if the positive reduced, do you think the leg will still be as open as it was? It will come closer. Do you get that? So that means that if you bring a negative charge close to a positively charged gold leaf, convergence will increase. Divergence, convergence will increase. Divergence will what? Increase. Let me go back to that. So please just listen again. So this body is positively charged. By the time I bring a negative charge closer, because of those that are there. So by the time I bring a negative charge closer, what will happen to this negative? The negative will run down. I mean, by the time negative run down, what will make this place do? This place will become neutral. And by the time it becomes neutral, what will happen to the leg? It will close. You know that the leg is opened wide because they are repelling. Abi? But now, by the time it becomes neutral, that leg will close. I hope you are following. This is not a class I want to waste time because you have a lot to cover. So that is what we call how you test. But now, let's imagine that I brought something closer. Look at this. Although I've done something like that. I brought something closer. I don't know what charge this guy carried. I brought it closer to this guy. And when I brought it closer, I noticed something. I noticed that the leg increased more. I don't know what is here, but when I brought it closer, I noticed that this leg increased more. If you are reasoning, what do you think has happened? What did I bring? You know, if I bring positive, what will happen? All this negative will run up because that positive will be attracting them. And when this negative goes up, this one goes up, then there will be build up of positive below. So there will be more positive and more positive. And what does that mean? It's increase its divergence. Do we get the analysis? So after class today, if you did not really get that, maybe those of you that is to stay out, you can quickly practice it together. So, but let me now form a table for you to understand that part. You have a gold leaf on the table. You have your body. The body you want to test, or the object you want to test. Then what will be the results? So let's be using this to explain. If my gold leaf is positive, that means that all of this guy is positive now, Abi. So if I bring a positive charge closer, so let's bring positive. So everybody look up. So if I bring positive, what will happen to the leg? Will it increase more or decrease? Increase. Increase. It will increase. Why? Because the positive will attract all the negative up. And by the time it pull all the negative up, then the positive leg will increase more. And that means that you will say that divergence will increase. Putting my arrow up means increase. So there will be increase in divergence. Do you get that? If it's opening the leg more, that means it's not closing it. Abi? So you can also say that convergence increases. So it's not converging. Do you get that? Now let's say still a positive electroscope, but now bringing a negatively charged body closer. With everybody. So if I bring a negative charged body closer, what do you think will happen to this guy? What will happen to the leg? Will it close or open? Close, because all the negative will run down. When the negative run down, what will happen to the leg? It becomes neutral. And at the end of the day, it will close. Do you get that? So that means that the divergence will do what? Decrease. And convergence will increase. When convergence means it closes, divergence means it opens. They can use that statement for that term. So now, let's say the gold leaf electroscope is now negative. I want to make it negative now, meaning that more negative than positive. So you know, more negative than positive, it will still repel, it will still be open. Now I now bring a negative charge closer. So if I bring a negative charge closer, what will happen to the leg? Will it increase? Will it open or close? Open. How did you know? The negative here will run down, Abi. And when those negatives run down, what happens to the leg? That means that the negative will build up below, and that will open more. Do you get that? So now that means if you bring a negative charge closer, you will get the same result. Increase in divergence and decrease in convergence. So yeah, when you have for a negative and you bring a positive, what will you get? Oh yeah, I want to end this part so that we go to electric field. Yeah? So when I bring a positive charge closer, now this guy is positive. You know, this guy is negative, Abby. So what will happen to if you should have been getting the story by now. So if I bring a positive charge closer, what will happen to the guy? All the negative will come up, Abby. And by the time this negative come up, that means it will reduce the number here, and that will make it closer a bit. The strength at which they repel will be lesser. Are you there? So that means that divergence will what? Decrease. Convergence will increase. Now look at something. Let's say this guy is neutral. You see why we say we must charge it now. Let's say the Coulomb electroscope is neutral. You now bring a positive charge closer. This guy is neutral. You know, if it is neutral, like this, the leg will be closed. All because nothing is repelling. Positive, negative, positive, negative, positive, negative, negative. And that's what you have. You know why the leg is closed, because nothing is repelling, everything is neutral, so it's balanced. Now, by the time I bring a positive charge closer, what will happen to the Coulomb? I bring a positive charge closer, it will open. How did you know? Because the positive charge will attract all this negative. And by the time the negative go up, what will happen to the leg? More positive. And what will make that happen to that leg? It's open. Do you get it? So which means that if you bring a positive charge close to neutral, divergence will increase, convergence will decrease. This body is still neutral, then I'm bringing the negative. So if I bring a negative to a neutral body, let's see what will happen. So if I bring negative, what do you think will happen to the leg? Don't cram anything, it's not something you can think about here. So if I bring a negative charge closer, what will happen to the leg? It's open because all the negative here will be sent down. That means this place will be more negative. And being more negative, it will open. So you can notice something here now. That means that divergence will increase, convergence will decrease. So which means that if you look at what we have done here, if you bring a positive to neutral, you will get a result. If you bring a negative to neutral, you will get the same result. So if you use a neutral Coulomb electroscope, you cannot achieve your result. Do you get that? The only thing that gives us opposite results is when the Coulomb are what? They are charged. Are you there? That's it. Very good. So that's what we have. So note something. When I brought positive, what happened? Divergence increase. When I brought negative, what happened? Divergence increase. So every time you bring same charges, divergence will always increase. It's another thing you need to know. You cannot be drawing an example, but your brain can still think in case you are stopped. But if you brought same charges, you're going to get increase in divergence and decrease in what? Convergence. If you bring opposite charges, you are going to get, you will see that the result here looks alike. Are you there? Yes. So that's that. So let's look at the next thing on electrostatics. We have used much time. So the next thing is this. We have what we call distribution of charges. Whenever you charge a conductor, when a conductor is charged, charges stay as far as possible. Away. They stay as far as possible away from each other. If I have this body now, this is almost like a spherical object. If I have charges here, all these charges will not stay inside, because why would we stay inside when we can still stay outside? They are all positive. This guy and this guy, you know, if the distance between them is close, the repulsion will be more. So they want to stay away as far as possible. So you can never have this arrangement. what you can have is that all the charges will be distributed outside. So when you have a body like this, charges are evenly distributed outside, not inside the conductor. Is that taken? That's what we call charge distribution. So this body has been charged, but the charges don't stay inside, they stay outside. That's why if you are in your car and lightning is happening, you cannot get electrocuted. You are protected inside your car. Even though it's a metal, you are protected. So charges are distributed outside. Do you understand that? So now the next thing is that if I have an object like this, one thing you need to know is that charges are evenly distributed on outside surface, but at pointed edge, charges are concentrated. Anywhere that is pointed, that's where you will have much charges. You just need to note that. So they can give you a question like this, that and D. Which one we have higher charge density? That means the number of charges per unit area. They can ask you, which points will have higher charges? D. Charges are always accumulated at pointed position. Is that taken? And don't forget, charges must not stay inside, they always must stay outside. All of these are questions you can see in your exams. So now, moving on from there, due to time, there are some things I'm trying to skip. And it's because of some of you that are just learning. That's why I'm actually listing them. If it had been those ones that did jam class with us, they know I will not even teach them all these things. I will not teach them. I will rather ask them to ask them questions. There are some deeper parts I would have taught. I will not teach these things. So now, from what we have here, let's just say we have one we call effects of charges, but I don't want to talk about that more. So how do you store charges? Because time is gone. You store charges using the capacitor. You use capacitor. You can also use what we call electrophorus. These are used to store charges. Electrophorus stores same charges. So to test for charge density, you use two elements majorly. You use a proof plane. A proof plane. A proof plane is just like a plate of metal like that. Then a proof plane and use a good leaf electroscope. So you just, this is what you do with this proof plane. You will just take it, use it to touch. You know, charges are more here. You will quickly, this is like an insulated handle. This is a metal disc. So you just take that insulated handle. You know, if this guy is neutral, you just use it to touch this thing. By touching it, that guy will acquire charges. When you touch it, if you touch it here, you can touch it here. You will now take it to a gold leaf and check. The divergence will tell you how much of the charges are around that place. So if I touch here and I touch here, which one do you think will have more effect on the divergence? Let's say this is A, this is B. Part A or part B? B. So if I take this and I use it to touch this, it will acquire a lot of charges. So when I put it on gold, the divergence will increase. But if I put it here and I put it on gold, the divergence will also increase, but not much. Do you get that? So that means that the charge density, that means the number of charges per unit area is more here than here. That's why you use this component. Do you get that? So that settles that. So what is an electric field? Let's go to electrostatics with, Coulomb's law. Are you through with this? So far so good. Did you get what we have talked about so far? When I'm through, we'll solve all the questions together. So yeah, let's go to Coulomb's law. Can I rub the ball? Coulomb's law should not waste our time. This part used to waste time because of all this drawing. And this is 10:30. And I still must talk about capacitor and current electricity today. So we can now solve all the questions here and there. Oh yeah. Can I rub the board? Yeah, let's move fast. The only thing I probably did not talk about here is just the effects of charges. How cars, trucks acquire charges. And they discharge the charge by attaching a small train to the base of a small chain to the base of the tanker. The tanker that is carrying fuel is moving in here. And as that tanker is moving, the air is rubbing against the tanker. So by friction, charges will be accumulated on the tanker, and it should not develop to a potential that can make the tanker to explode. So they will now put a chain at the back of the tanker. So as the charges are being accumulated, it is earthed, like grounded. So the charges are being passed down through the small chain. They asked in UI past question, UI post 2 last year actually, they asked that the use of the chain that is attached, that's a jam question. The use of the small chain that is attached to a tanker, what is the use? They said something like A, to prevent electric shock, to prevent explosion, to prevent blah blah blah. So you note that aspect. Then another thing is lightning. Why is it that when lightning happens, you see a flash when lightning happens before you hear thunder? So you see a flash of lightning before thunder, or thunder before lightning. Lightning before thunder. The speed of light is more than the speed of sound. So you hear lightning, you see lightning first before thunder. So when lightning happens, it is due to this. Charges are built up in the layers of the cloud, and those charges are suddenly discharged during rainstorm or during some seasons like that. And it's not because God is angry at you and God wants to strike you, center of your head. But that lightning can catch a house, and the house can catch fire. And that's why we use what we call points action. This part here now, accumulation of charges here is almost called like points action. And this is used to prevent houses from getting burnt down by lightning. So there will be a metal, a pointed metal. That pointed metal is usually inside the house, around the house. They used to dig it in the ground, so that when lightning happens, it's the one that will collect all of those charges at the pointed edge and put it on the earth. So you can read more about lightning. Those are just the remaining things to complete this note. Lightning and the effects of charges. That's all. AI is there, YouTube is there, a lot of things you can use to learn it, just to have knowledge. So can I rub the board now? Oh yeah. So Coulomb's law. Now we have been talking about charges since morning. All of the experience here now will be used in the next law we want to talk about. So what is the rule of electrostatics? Like charges repel, or like charges do what? Attract. So now, to start with electric field, the next thing to talk about will be Coulomb's law. That's the first thing. Coulomb's law. Coulomb's law sometimes is called law of electrostatics. Coulomb's law is talking about I have a positive charge and I have another positive charge. What did you say will happen to them when we bring them closer? They will repel, Abby. And Coulomb's law is now telling us that how much of repulsion will you feel? So it's a way to calculate that. So Coulomb's law is telling us that the force of repulsion between them, if they are separated by a distance, what will be that force? Of repel. If you have a positive and a negative, what will be that force? Of attract. She gets. That's Coulomb's law. So Coulomb's law states that the force of repulsion or attraction is directly proportional to the product, and don't forget this definition. It is the force of repulsion or attraction between point charges. Point charges. The force of attraction between 2 point charges or repulsion, the charge can either be positive or negative. The force of repulsion or the force of attraction between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So introducing our constants, that's the constant is K. That's Q1 multiplied by Q2 over R squared. Majorly OAU students, this is an important formula for OAU students. If you are writing OAU physics. So now F is equal to KQ1 Q2 over R squared. Do you get it? That's the definition. The force of attraction or repulsion is directly proportional to the product of the charges and inversely proportional to what? To the square of the distance between them. So F is equal to KQ1. What's your K? K is given as 9 times 10 raised to power 9 Abi. Newton meter square per coulomb. Per coulomb square. That's the units. Your F here, is called your electrostatic force. That's your F. The Q are the charges. Then R is the distance between those charges. Let's say this is Q1 and this is Q2. So the distance between them. So you need to now note something. If I ask you a question here, this is Q1, positive. This is Q2, positive. Q1, same magnitude of charge, and Q2. This is the distance between these guys, and this is the distance between these guys. So let's call this R1, and let's call this R2. Now, if I ask you, if they have the same magnitude of charges, which one do you think the forces will be more? Is it F1 or F2? What type of force will you have here? Repulsion or attraction? Repulsion. Which one will it be more? Which one will the force of repulsion be more? F1. Because from this formula, F is inversely related to R squared. That means that the higher the R, the lower the F. The lower the R, the higher the F. So from here now I can say that F is inversely related to R squared. And if I introduce my constants of proportionality, I can have my R squared. So I can say F1, R1 squared is equal to F2, R2 squared. So I can calculate my F2. Now, it's an important formula you need to know. Let's take a quick question. Drill. What will be the force of repulsion? Another thing you should not forget, between 2 point charges of, I already said repulsion, so you should know, 6 micro Coulomb. The unit for charge is Coulomb. 2 point charges of 6 micro Coulomb separated by a distance of 10. Another thing you have to be careful of is units. If I say 10 micrometer, because in post-UTME what they want to test the most is your sense. So you must know how to convert the meter, micrometer to meter. It's important. But don't let me use micro because I already use micro here. So let's say 10 picometer. You don't know what pico is. It's a bit of problem, and which it shouldn't be a problem. So now your K is equal to 9 times 10 raised to 9 Newton meter square per coulomb square. So now from what we have here, how do we solve it? we have 2-point charges Q1 and Q2. Q1 is 6 microcoulomb. Q2 is also what? 6 microcoulomb. Is that taken? So I can say my F is equal to KQ1, Q2 over R squared. And that's going to be, what's my K? 9 times 10 raised by 9 multiplied by my Q. Q1 is, you can just multiply by 2 since there are 2 of them. Is that correct? Square them, sorry. So that's going to be 6 times 10 raised by minus 6 micro, having all squared. Or you just multiply them together. Over, you convert this to meter. Equal is what? Don't forget this square. 10 is, so 10 times 10 raised by minus 12 all squared. So in your exam, you will not be allowed to use calculators. So you must know how to deal with standard things. You can just simplify it as much as possible with what we have here. This will be like, don't even multiply through first. You can do, in order not to waste time, you can do everything without your calculator. So you can just say 9 times 10 raised by 9 multiplied by 6 times 6 times 10 raised by minus 2. Is that correct? All over, you know, that's 100. And this is going to be minus 24. Adding 100, so that's minus 22. Is that taken? Do you understand that? 10 raised by 2 is 100. 10 raised by minus 24 times 10 raised by minus 24 is 10 raised by minus, 10 raised by minus 12 times 10 raised by minus 12 is 10 raised by minus 24. So this is 100. 100 minus 24. What's the mean? So that's what we have. So when this one comes on, it turns positive. 6 times 6 is 36. I mean 36 times 9. It's easier to do that. Anything times 9 is easier. 9 times 6, just remove 1 from 6. That will give you 5. Then add anything to it to make it 9. That's 54. So 9 times 6 is 54. You write your 4. 9 times 3, remove 1. That's 2. Add 7 to it. That's 27. Plus 5, that's 32. Yeah? That's correct. So it's easier. So there are some things you must learn to do without calculator in the exam. Anytime you are multiplying 9 with a number, reduce that number by 1. If I say 9 times 6, reduce 6 by 1, that will give you 5. I mean, add the number that will complete 9 or 4. The answer is 54. 9 times 9. Reduce this by 1, 8. What will you add to this to make it 3? The answer is 81. She gets. So there are some things you have to do in the exam now. It's not everything that you will be looking for calculators to do. And you have to be. First thing we always do in post-UME class is how to solve without calculator. So you can solve the rest on your own. So now, the next thing to know is what we call electric field. So now that you know Coulomb's law, you can practice questions on these two. So now, what do we call electric field? That's the next thing. Are you there? So you can complete that one. 10:45. So electric field is defined as the region around which electric force is felt. So the region around the charge. Region where electric force is felt. Please, just for simplicity, this is positive. If I bring a positive charge closer, this guy will repel this guy. Abi? Because it's in the field of this guy. So this guy will feel a force. Both of them are feeling a force here. But do you think that if I have a magnet, let's say this is a magnet, and this magnet creates a field. If I bring another magnet, let's say magnet B, magnet A. If this magnet is here, and this magnet only creates this field, do you think they will attract or repel? Because this guy is not in the field of this guy, so it's not going to feel any magnetic force. Do you get that? But by the time this guy enters this place, then it's already looking for trouble. It is either it is attracted or it is what? Repelled. Do you get that? So let's say this is a charge now. This charge has created a field around itself. So if I bring a positive charge here, they will not feel anything because it is not in the field. But by the time the positive charge enters, what will this one do to it? Send it out. So that is what we call electric field. It is the region around an electric charge where electric force is what? Is felt. So this is a field. Do you get that? But how do we determine electric field? We have what we call electric field lines. Electric field lines. So let's quickly look at the properties of electric fields. So now if I have electric field, we don't just draw circle like this. For electric field, number one is it moves radially outward for positive. The field moves radially outward for positive. So whenever you have a positive charge, always know that this is what you are going to have, an arrow like this. I hope you are here. So please note, if I want to ask what charge is this guy carrying, all you are just going to look is the arrow. If the arrows are pointing out, then you have a positive charge. Do you get that? So I might not show you this. I might say, what is the charge carried by this guy? The moment you look at this arrow, you will tell. So for positive, the arrows always point what? Outside. That's what this word means. Do you get that? So that means this guy is positive. For negative, it is inside. So for negative, what will happen? Negative is radially inward. Are you there? So for negative, it moves radially inward. So make sure you look at those arrows. So from what I have here, so everybody, what is the charge carried by B? What is the charge carried by A? So just look at the arrow. Is that taken? In the second case, what is the charge carried by A? What's the charge carried by B? Do you agree?
Yes, sir.
Yes. For A, what happened? The charges are moving outside. You can see the arrows are going away from A. That shows that A must have been what? Positive. For B, you see that most of those arrows are going inside B. That means that B must have been what? Negative. So let's move on. So that's what the two statements mean. For positive, it moves radially outward. For negative, it moves radially inward. Number 3. Electric field lines. Electric field lines are imaginary. They don't exist, but they are imaginary. So they just show the direction in which a test positive charge will move. Are imaginary and shows the direction. They are imaginary and shows the direction a test positive charge moves. So how did I know this one will be radially outward? It's because I used a test positive charge. Let me show you what that means. So it is conventional to use that. So let's say I have a positive here. Are you there? Now with that positive, I'm now bringing a test positive charge. We call it a small test positive charge. I said the electric field lines are imaginary and all they show is just the direction a test positive charge moves. So this guy now, I want to know how will the field behave. Then I bring a small test positive charge closer. What will I notice? This guy will be pushed away. Abi? That means that this guy is pushing this guy in this direction. That's what that statement means. So if I bring positive charge, it's always send it away. So the arrow is always outside for positive. If I bring a negative charge closer, I mean the same test positive charge close to a negative, what will happen? So that's, do you get that statement now? So if you bring it inside. So the statement is just, let's just have a line to represent it. But it's imaginary. But it shows the direction in which a small test positive charge will move. So that's an electric field line. Number 4, electric field line do not cross. They do not cross. You know, it's always move from positive to negative. So if you have positive and negative, they will move inside each other. If you have negative and negative, they will repel. So they don't cross. They can never come across. Number 5, another thing you need to note is that aside crossing, there was something that came to my mind the other time. That I was saying. Let's go on. So the next thing you need to note is that uniform field are equally spaced. They have equal strengths at every point and are usually parallel. So we have two types of electric fields. The uniform field is equally spaced. I remember what I wanted to say now. It's equally spaced. I wanted to just say it's a monopole, not a dipole, but I'll come back to that. Yes, I forget, that's why I said it again. So, if I say the field is uniform, these are the electric field lines now. Then, let me just read this way. Let's say I have positive, 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 just like in a capacitor. Negative, negative, negative. Field will always go from where? From positive to negative. Abi? That's the arrow. So it will always go like this. So look at this field now. They are equally spaced, and they are. So if I bring a positive charge here, it's the same thing it feels here that it will feel here because the strength is the same. You will understand with non-uniform now. For non-uniform, if the field can be like this. If I bring a positive charge here, it's not really experiencing much force because of the space. But if I bring it here, a lot of things are going to act on it, push it all out together. That will take us to the next statement. So when the fields are non-uniformly spaced or non-parallel to each other, then we say it is a non-uniform electric field. Is that taken? Are you following? Yes, sir. So number 6, we are still on the properties of electric field. Number 6, electric field can be a monopole. What does that mean? Positive can be on its own. You can separate them. Negative can also be on its own. Another thing is that the closer the field, the more the strength. The closer the field, the more the strength of the field. So if you look at this place now, point A, point B, point C, point D. So if a charge is at that different positions, where will it feel more repulsion or more attraction? Is there a point A or point B or point C or point D? At point D, because the fields are closer there. So it's the experience. And for the field to be closer there, it means that a lot of field and line are running through that part. So let's leave that. Those are the properties you need to know. So the next thing is what we call electric field patterns. Electric field patterns. Electric field patterns is just talking about the representation of the electric field. And we draw electric field pattern using, it is drawn using a small test positive charge. A small test positive charge. That's what you use. Is that taken? So if you want to draw electric field pattern, use a small test positive charge. They can ask you that. So now, how do you draw a positive pattern? We can draw for like charges. So if you want to, there's one more statement here, but let me finish drawing this. So I'll tell you the statement. For like charges, let's say I have a positive charge and I have a positive charge. The two of them, I want to draw their pattern. For positive charge, you know, normally positive is supposed to be going like this. And this one is also supposed to be coming like this. But because they will repel, so they cannot cross. So what you will just notice is as this one is coming, it will move away. Or because it's encountering another positive. So they will repel. But you can see the way my arrows are. Which means there are fields here, there are fields here, there are fields. Except at that center. Why is there no field at that center? Because they are repelling. Abby, they are repelling there. So at the end of the day, this center is called your neutral point. 30 level, be open. That center is called what? Your neutral point. So they can ask you, they can just draw it and say you should show where the neutral point is. And when you say neutral points, it means that you are not really going to feel any force because there is no field there. So if I put any charge here now, that charge will not feel anything. So we call it neutral point. So NP is neutral point. All these are things you need to remember and note. So it is the point where electric force is not felt. That's the neutral point. The next thing to look at is this. Are you following? What if they are negative? Look at this diagram. Can you tell me what A is and what B is?
Negative.
How did you know both are negative? Number one is that the arrows are going inside them. Abby, do you get that? And they are repelling. Both of them are negative. So the moment arrow, you can see this arrow, they are going inside. Look at for positive. I drew the arrow that they are going what? Outside. Again. So this is what? Negative. This is also what? Negative. So those are like charges. For unlike charges, let's quickly draw. I've drawn that before. So you are most likely not going to have a neutral part for this one. So, what's your A and B here? A is what? A is positive because the arrows are moving outside. Abby, and B is what? So by now, we're practicing questions. Can we move on? 11:01. Your normal break is always by 11:30 now, Abby. But we have no break, so it's here. So it's about oh yeah, can we move on? So the next thing is this. What's that one? Let's talk about electric field strength. Electric field strength. Then, if they say that, how do you determine the direction of the electric force? You determine the direction. The number of lines tells you the magnitude. Please, in case they ask you. You know I told you that it will be small at the points. Magnitude is talking about the number of lines. Like the strength will be more where the lines are more. But if you're talking about direction, if I bring a positive charge here now, how will that positive charge go? You will draw a tangent to this line. So that tangent shows that the positive will go away that way. So to determine direction for electric field lines, we use tangents. Tangents to the field. So you draw a tangent to the field in order to determine the direction. You know what a tangent means? Just if I say the charge is here now, you draw a tangent to that place. Check it. That's what that statement just means. So to get the electric field lines, just for ways for you to quickly grab. So you can add this, that the direction of the electric field line or force is determined by tangent to the field. You can add that to the properties when you have the space. So what's an electric field strength? Electric field strength is defined as the force acting per unit charge. Are you through with this part? Oh yeah, are you through with this part? So that I can explain that part quickly. Please, I hope you are getting something.
Yes.
You have to finish everything electricity today. It's not much. Oh yeah. So that if we have another class, we try and do everything magnetic. It's because of those of you that just learned. Normally, for my JAM students that came around, this is not what we should be. I've taught all of these things. It's not what we should be talking about again. But it will serve as a revision for them and maybe pick up one or two things that they didn't get. So can we move on? Oh yeah. Are you true? So electric field strength. When you're talking about electric field strength, the word strength, we already said a charge is going to create things. Do you think that we have equal strengths? No. It's the same thing we're talking about electric field. So a bigger charge will create more. Like this one now, all the field will be like surplus, and anything that comes around here, send it away. But for a smaller charge, it can just create a field, but the field will not really have that strength. Do you get it? So now, if this charge, let's call this charge Q, is creating a field around itself, then I bring a small test charge, positive, closer to this guy. You know, this guy is going to experience a force. The force can either be repulsion or attraction, depending on what this guy is having. So if this guy is positive, what will he do to this guy? It will repel it, Abi. So now, so you are bringing the small test charge. It's already in the field of this guy. So the intensity, the strength at which it will send it away is what we call the electric field strength or electric field intensity. Do you get that now? So that means that the force acting per unit charge is what we call what? Electric field intensity. The unit is Newton per Coulomb or volts per meter. You will see why it is volts per meter soon. And you now remember how this guy now is small q. This guy is capital Q. You need to understand some of these things, especially when you are solving questions. This small one for me now is my test charge, not the capital Q. So let's see how capital Q will come in. So if F is equal to KQQ, over R squared. Do you know that? Right? So now bring it into this formula. So my E can be equal to KQQ over R squared multiplied by 1 over Q. Abi? Now, my Q. So what do I have? KQ over R squared. So you can write this formula again as, sorry. So your E can now be equal to KQ. That E has factored in his own strength. I help you in the exam to express yourself. The higher the charge, the higher the strength. It provided the distance remain constant. So now, we still need all of these things, especially if you want to get to the advanced part. You will need them to express a lot of things. With that, since I came, I was trying to allow you to cut. So can we move on? So now, you can see these two formulas are important. So sometimes they can give you, they might not even give you postute CME. So sometimes the postute, during the, I still remember Dr. Peter told me in UI during their set, they did not give them Q or G. But you have to know it offhand as you are going in case. So they might want to give you, but if, in case they did not give you, don't now say I did not remember what Q was. So that's that. So the next thing to look at is what we call electric potential. That's a direct formula and it's a simple thing. Electric field intensity is defined as the force acting per unit charge. So electric potential is defined as the work done. From the formula you can know the definition. It is the work done. Electric potential is represented as V. It is the work done in moving a unit charge from infinity to a point. So electric potential is simply the work done in moving a unit charge from infinity to a point. That's the definition. The work done in moving a unit charge from infinity to a point. Electric potential is scalar. Electric field intensity is vector. You need to note that. So now, from what we have here, what is work done? Abi? So now, what is force? KQQ. Let me use one capital Q. KQQ over R squared times distance S. Distance and distance. So that can give me KQQ over R. Abi? So that's work done. So bring work done here now. All those formulas I'm putting in brackets, they are the ones you should know. So V is going to be my work done. That's KQQ over R multiplied by 1 over Q and the Q and the Q. So V is equal to KQ over R. So please, this formula always carry negative when you see it. And don't forget, you might see it in many cases. K is equal to 1 over 4 pi E naught. E naught is called permittivity of free space. I think they've used that a lot to ask questions before. So you just need to note this. Electric potential always carry negative. The body is being brought from infinity. If you derive this formula using integration, you will get negative. Yes. And the negative is the symbol that potential is decreasing. It's a symbol. There's a lot to talk about there. Let me just use this. I can use this analogy that from the Earth's surface, I'm bringing a body, just like gravitational potential. Bringing a body, as I'm taking the body up, I'm increasing its potential. As I'm taking it up from the Earth's surface. Which means that if I'm taking it from the sky now to the Earth, what am I doing? I'm increasing the potential. So if I'm bringing it from infinity down to a point, I'm decreasing the potential. Something always go from higher potential to lower potential, not from lower to higher. So, but that's just the point. You just note this. that this formula, so if they give you this formula in an equation, that you should pick the one that is correct in option, pick the one that has what? Negative for electric potential. So now, what is the relationship between electric potential and electric field intensity? Both of them. What's the unit for electric potential? They can ask you. The unit is volts. But that volt is called joule per coulomb. Because especially those of you writing UI, they won't ask you anything technical. They will just ask you in a way that, I mean, anything beyond your level, but they will ask you in a technical way. So, what's the unit of electric potential? Volts. Which of the following can represent the unit of electric potential? Volts. Roman figure 1, Roman figure 2, joule per coulomb. Then you are now lost. Joule per coulomb is the same thing as what? Volts. Because work done is what? Joule. And coulomb is what? Charge. Is that taken? So you can also say it is joule per coulomb. That's another unit. So now let's move on. What's the relationship between, and what we are saying here might not necessarily apply to this. We might get to some other aspects and it applies. That's where knowledge comes in. So now the relationship is this. Remember that E is equal to KQ over R squared. Do you agree? E is equal to what? KQ over R squared. Now, I can still write this formula as KQ over R multiplied by 1 over R. Do you agree? What is my KQ over R? V. So I can now say this formula can be written as V over R. So that's another important formula. So this is the relation between electric field intensity and electric potential. I'm not going to talk about multiple charges, but it's needed. But it's not needed for your post-it most times. I won't ask you. But where you can ask you this. If the charge, maybe I should just, I don't even know, I'm still coming around to talk about some other things. But I just want all of us to have all the necessary idea. So that when I now come, all these parts now, if I come back, maybe after my entire exam now I come, I will just pick maybe some deeper parts that I know that some of you need to know. In this class, I might not express Kirchhoff's law. I might not express electric field for multiple charges. But before then, you must have known all of these ones and practice very well. So by then, if I come, I'll just do 1 or 2 things about multiple charges. You can see it in UAE post-it, but you can't see it in UI. You can see it in UAE. So in every other school, what we have talked about, just expressing yourself is enough. So if I come, all those Kirchhoff's law and multiple charges, talk about them. I will just know those are the parts I want to touch for. So now let's move on. Now, I think there's nothing much again than electric potential energy. And electric potential energy is simply defined as the work done itself. So electric potential energy is different from electric potential. So electric potential energy is the work done in moving a unit charge, but it is the work done, not the voltage. Electric potential energy is equal to work done. Just the work done. Because of the unit charge, so you don't put that unit charge. It is just equal to the work done. So what would be the unit for electric potential energy? The word energy, joules. And anytime you're talking about potential, it is scalar. It's scalar quantity. Electric field strength is vector quantity. But electric potential is scalar. Is that taken? So that's all. Those are the things we need to make for electric field, electric potential. Quickly calculate this question. Determine the electric potential. Electric potential for a charge of 3 microcoulomb. Move through a field with work done 500 kilojoules. Determine the electric potential for a charge of 3 microcoulomb move through a field of 500 kilojoules. Question 1. You don't need to add the negative in your answers if you don't find the answer of those things. So, number 2, a charge of 10 microcoulomb is moved by a force of 200 Newton. What is the intensity of the field moving the charge? What is the intensity of the field moving the charge? All these are basic questions, theoretical. Number 3. A charge three microcoulomb with an intensity of 200 volts per meter. It's an intensity of 200 volts per meter. Performs the same work as another charge of 800 volts per meter. Determine the charge worked on by the 800 volts, keeping other factors constant. Number 3. Number 4. Which is true? Which is true? Roman figure 1. Electric field intensity EFI is measured. Electric field intensity is measured in volts per coulomb. Volts per coulomb. So, electric field intensity is measured in joule per coulomb. 3. Detergents to a field determines the direction of a field line. Four, the smallest positive charge. The smallest positive charge. The smallest positive charge moving close to a charge Q as its potential energy decreased and kinetic energy increased. So let me dictate that number 4 again. The smallest positive means probably force. Roman figure 5. What have I taught you? For charging my both A and B are neutral. At the end of the day, you have to tell me what A would look like and what B would look like eventually.
Second one, it says 300 of you. Because we're going to now. You did. Use it because of that. Which one do you use? Because of that. You introduce the constant. Let me see how you do it. So what's your working? So that
F is constant, so that's E1, Q1. Okay, enough of your values.
E1, Q1 is equal to Q2.
Since you're looking for Q2.
What did you say you got again?
0.75 times 10 to the power minus 6.
Times what?
10 to the power minus 6.
So those are 8 questions, and the 8 question covers almost everything I've talked about today. Not all, but almost everything. So can we move on? So the first question, determine the electric potential for a charge of 3 microcoulomb moved through a field with work done 500 kilojoule. The second question, a charge of 10 microcoulomb is moved by a force of 200 Newton. What is the intensity of the field moving the charge? Number 3, a charge 3 microcoulomb with an intensity of 200 volts per meter performs the same work as another charge of 800 volts per meter. Determine the charge worked on by the 800 volts per meter, keeping other factors constant. Number 4, which of the following is true? So answer if it is true or false. The electric field intensity is measured in volts per coulomb. Electric field intensity is measured in joule per coulomb. Electric field, the tangent of a field, the tangent to a field determines the direction of a field line. A small test positive charge moving close to a charge Q has its potential energy decreased and kinetic energy increased. Moving close. Move. Change the moving to move. Okay, moving. Moving is okay. That's progressive. So number figure 5. In charging a contact, opposite charges are obtained. So number figure 5. Determine the charge attained by A and B. Number 6, the use of small chain attached to a tanker. Why? What is the use of small chain attached to a tanker? What do you understand by point action? And 2 charges are separated by a distance 2 femtometer. You have a question? Okay. 2 charges are separated by a distance 2 femtometer and a force F and on the and a force F acts on them. What is the force when separated by 8 micrometer? Those are same charges. So what is the force when separated by 8 micrometer? So are you there? So when we are through with electricity today, on Friday we do everything light. So I'll teach you how lenses operate, everything about lenses, and all the questions you can likely ask you. So please, let's practice them. For the OAU students, there are still 1 or 2 things we need to talk about, which I promise you I'll talk about it. But everything I've said, we cover everything in electricity. So even if it is JAM you are writing, it is any school of nursing, it is OAU, it is UI, any school you are writing, what we have done so far on this aspect, we have to cover them. We just need to practice. That's the only thing. We just need to practice. So are you through with the questions? Oh yeah, you can practice them on your own. The time is 11:32. Should I give you a short break? Yeah. Then I will continue. Because I want to quickly talk about capacitors and current electricity. Should we continue with our class? Yes. Yeah, let's go on. Are you through with this? No. Fast, no, be fast, be fast. To some extent, what we have done so far, did you understand?
Yes.
The only problem is that I didn't take my time to start giving you notes. That's just the problem. But you know you don't have much time. And even if you are writing down, you should be happy. Because just go and carry either today's physics or your jam past question and start solving. Before the end of this month, you are ready for jam. So you will now be working on yourself. Those are the things. If you see people scoring 300 and above, they did not just start. They did a kind of repeated practicing. And that's what helps them. So don't think that everybody just gets it just like that. All of these things are not tough if you can practice well. I hope you know what to do with all of the questions. Do you want me to explain any one of it? At least you can do. So I will provide the answers. And if you are probably watching online too, maybe you're watching the class live online. Are people online? Or should disconnect everybody? Should we disconnect you or we should? So if they are online, you can leave your answers in the comment section. So provide you the right answers. If I try is online. My guy is online. So are you true? Almost. So can we move on now? Almost. Oh yeah. So at least by the time you finish this, do lenses, and you have done techniques. But because of those that just joined, we'll find a way to quickly summarize just the important part. People should have been through now. Yeah, let's move on to capacitors. Your experience now will be needed for capacitors. What we just finished doing now will be needed for capacitors. When we are through with capacitors, I will also give you all the questions they can ask you on capacitors. And we'll now pick your normal questions to solve from textbooks. All these ones, I'm just coining them from my head. I did not prepare for them, so I just have to quickly coin them. Just to help you touch everything. So to those streaming online, if they want, so people streaming online, if you want this to continue, you can leave it in the comment section. If you don't want it to continue on Friday, we'll not connect you. We don't want to disturb you. So, but if you feel you want it to continue on Friday, you can join online. Same time, same venue. Can I rub the center now? Oh, yeah, now. Nasro. Olamide, have you seen your twin sister? Do you know that you people look alike? I thought you were in hostel when I first saw her. I thought you have moved to hostel. The only thing is to watch your love. Nasro, what's your name? Asha. This is Asha. Aisha. Baby daughter. How are you? Are you getting anything? Are you happy? Are you sure you are happy? Don't worry, you'll be fine. Take your time. Things get better with time.
We have like
Where is this? Now sitting at this is more than you see that. I saw him open up and that. Biggie. I'm looking for you. Okay, I'm following you guys. You people should start. So are you true now? So let's quickly talk capacitor. Then after capacitor, we talk about current electricity. And that will be all for electricity. We still talk about applications of electricity. Are you true? So the best you can now do is maybe after the class today, those of you that used to form groups, maybe because of those that just joined, after the class you can just solve questions on everything today. Everything today after the class. And if there's any part you do not understand, you can also send it to me to explain better. Are you So let's come back. So everybody stand up, stand up. Oh yeah, don't waste time. Everybody stand up, arise, arise. In my class, we act like soldiers. You don't act law. You act like soldiers. Watching Joko be Yaruka. If you're happy and you know, clap your hands. You people are not. You want to go? If you're happy and you know, wave your hands. If you are not waving, and if I start this class, if you're born, you will sleep. Wave your hands. If you're happy and you know, and you really want to show, if you're happy and you know, give me money. People cannot drop something. We are drop chocolates. Did you bring rice and spark? Drop it. After sermon, there's offering. After class, there's offering time. Offering time. Oh yeah, everybody jump up. Oh yeah, oh yeah, oh yeah, oh yeah, oh yeah, oh yeah. Up. Let the blood flow again. Some of you cannot even jump. Jump. Oh yeah, oh yeah. Are you ready? Those of you. So if you feel you are feeling sleepy, remain standing.